This section's on exponential and logarithmic models. So we're going to look at what some of the various graphs look like, and then also talk about when you would see them, and then work some problems that relate to those types of models. So the first one that we have is a logistics growth, or a logistics model. And notice that it's a elongated S-shaped curve. And we'll see an equation that kind of helps us understand why it is what it is. The second one is, and this is, logistics are often used with the spread of diseases. It's also was used by Sam Walton, founder of Walmart. And when he wanted to know how long to keep an item on a shelf, he would plot its sales. And it would gain traction, and then about this point, it's starting to pivot, and it's not going to be a hot seller anymore. So we would pull that item from the shelf or put it in a different location, and then use that prime location for his newest item that he wanted to sell. So that's a logistics model. Exponential decay, carbon dating, depreciation are all modeled by an exponential decay problem. Those are things like how much is your car worth after a certain number of years? How much is a copier worth? How much radioactive carbon is, or how long is this, how old is this fossil type of problems? Then we have exponential growth. We've been talking about those with population growth in our investments, our E equals P, or A equals P to the ERT types of problems. And then Gaussian or bell curves is something that you studied a little bit last year when you were talking about the norm reference tests and the mean and how many standard deviations you were away from the mean. So you worked with those a little bit in Algebra 2. So the other two are natural log. This is a relatively slow growing natural log for population growth, the growth of investments, and then also a Richter scale model. That's our common log, and that's what we use when we're determining earthquake intensity to see, how strong that earthquake was in Oklahoma not too long ago when we actually felt it here in Nebraska. All right, so here is some data that I saw on the CDC's website back in 2014. This was about the time that my son was in pre-calc, and I ran across the data. I'm like, hey, finally, I found some data, the actual numbers, not so much something that someone has already plotted. And I want to see if we can do just some prediction to see what, where this particular outbreak is heading. So when I plotted the data, back in March 24th of 2014, that was when they first made the announcement that there had been 86 suspected and confirmed cases of Ebola. In Sierra Leone, and there were several countries in Africa that had this outbreak. And so then by March 31st, they had another public service announcement, and that was 6 days afterwards. There were 120 cases and so forth. And then by July 30th, they were at 1,440 known, confirmed, or suspected cases, and so forth. So what I wanted to do, this was around the 18th of September when I had seen that last bit of data. I wanted to see, well, how many cases would there be by the 30th of September? How about the 31st of October? How about November? How about December 31st? Okay, so I took that data and I plotted it on my graphing calculator and came up with an equation. And then I plotted it in Excel and came up with an equation. So the equation in Excel is a little less cumbersome. Show you what it looks like, and it's actually on your sheet. If I can get to my next slide. The Excel equation was y equals 85.713 e to the 0.0218x, so fewer decimals. The equation that came from my graphing calculator was 85.7130987 times 1.022057209 to the x power. And those were the curves of best fit that modeled this particular outbreak at that time. So it was looking like exponential growth at the time. And what researchers are hoping for when they're plotting this is to figure out when it's going to turn into a logistics curve. When is it going to start tapering off? Do we need to send more aid workers, more medical professionals, more nurses, more drugs and so forth, set up more clinics, or are we kind of getting to the tail end of an outbreak, and can we, start to put our resources elsewhere? And a lot of the Ebola money that was marked for Ebola has now been switched now to the Zika virus, and so we'll see, how that plays out, and that seems to be a greater threat right now. So we're going to take these two equations and decide or find out how many cases we think we'll have by day 190. Okay, so we'll do a backward prediction to see how many cases based on the model would there have been on the 190th day, September 30th of 2014. So when you look at a model, you have to decide, A, what does the y stand for and what does the x stand for? So y stands for the number of cases, and I need to reorient my board. And the x stands for the day since the initial report was made, number of days since the initial report. So y is the number of cases, and x is the days since the first report. Okay. So the nice thing about it is when it's in this form, it's pretty easy to plug in 190 to figure out what our answer is. So we'll plug in, we want to know what is y when we have 85.71309,867 times 1.022,057,209 to the 180th. Okay, so we'll plug the, 190th. We'll plug those numbers in and see what we end up with. So we start with our 1.022,057,209. Good question. Great question. If we used a smaller equation, would it give us the same question or same answer? So somebody pick, let's have one person do y equals 85.713 times 1.022 to the 190th. Okay, and we'll see how close those answers are, because maybe we don't need all of these, that level of accuracy. Oh, this one? We're going to look at this one as well and see how close these two come. Okay. All right, so somebody do this one for me. Whoever wants to do an easier one. And then we'll plug in the 1.022,057,209 to the 190th. And take that number times 85.71309,867. So we're predicting this one comes up with 5,412 cases. Is that what everybody else got? Okay. And let's try this one. 1.022 to the 190th times 85.713. And we got 5,354 cases. So do you see that rounding can make a huge difference in the number of cases that we predict? Okay, that was rounding to the thousandths place. Okay, so now let's try this other one. How many cases will we have if we take 85.713 times e to the 0.0218 times 190? So we do our power first, or e to the, and then 0.0218 times 190, because our calculators are smart enough to know order of operations. And then we take that times 85.731. And this model I did this correctly, came up with 5,395 cases. Okay? So, relatively close, right? On day 190, this one was closer with its rounding than the other. Okay? So that's the easy part, just plugging in a number for x and evaluating. But what about this second piece? When will each of them reach 10,000 cases? On what day? How do we solve that? Now we have our y, right? And we need to figure out what our x is. Okay, so we're going to say 10,000 is equal to 85.7130986 times 1.0220572009 to the x. How do we solve something like that? Divide by our 85, right? Okay, so when we do that, 10,000 divided by 85.7130906 gets me 116.668, and I'm not clearing my calculator here. I'm just writing down a partial of it so that I don't have to write it all out. And I'm saying that that's equal to 1.022057209 to the x power. Now I want to get to my x, and it's an exponent. So the opposite of exponential is log. The inverse of exponential is log. So we want to take a log base 1.022057209, right? So we'll take that log. Of 116.668 and do the same thing on the other side, right? So on the right side, we just get plain old x. And on the left side, we're taking change of base formula, right? The log of 166.668 divided by the log of 1.022 and so forth. So take the log of whatever was in your calculator, log of answer, close your parentheses, and divide by the log of 1.022057209. And we get 218 days. Okay. Crazy numbers, but in the real world, when we're dealing with real world data, that's the type of thing that you deal with. Okay? So let's do the other side of it. Now we want to say 10,000 is 85.713 e to the 0.0218 x. How do we solve that one for x? Divide again, right? 7. Okay, so 10,000 divided by 0.713 gets me 116.668. Again, I'm not clearing my calculator. I'm just going to leave it in there. But I'm only writing a portion down. And that's now e to the 0.0218x. So now, how do we get to our exponential when we have an e for our base? The log base e, right? The natural log. So we'll take the natural log of both sides. Okay, so when I take the natural log of what was in my calculator, natural log second answer, close the parentheses, I get 4.759 roughly is equal to the natural log of e goes away and we just get our power, 0.0218x. Now how do we get the x by itself? Divide. So we'll divide by 0.0218, and this number divided by 0.0218, this is now the time that we round. So we say 218 days. And they came up with the same answer. Okay? So both models are predicting roughly the same type of curve, same kind of equation. All right, questions about this slide? All right, so next one says, guess what? Population growth. When we're looking at that, we can have a model like y equals 1.8 e to the 0.026x, where x equals 0 corresponds to 1980. And we need to figure out when the population would be expected to reach 2.5 million. Okay? So where does our 2.5 million go in? X equals 0 is 1980. That's our time, right? Okay, so we're trying to find our time, what year, when it's supposed to reach 2.5 million. So the 2.5 million is your y. And we'll have e to the 0.026x. How do we solve that? So we divide by 1.8. And we get 1.38 repeating. Okay. Now, how do we get rid of an e when we have e to the 0.026x? Use the natural log. Natural log of 1.38 repeating is the natural log of e to the 0.026x. So on the right-hand side, I get 0.026x because they're inverses of each other, and the natural log of my previous answer is 0.3285. And so we want to get the x by itself, we divide. And I have not cleared my calculator at all. I kept everything in there pristine. So when we get 12.6 years, that's really 13 years later, right? So what is 13 years after 1980? 1993. Okay, we don't really ever say 1992 and a half or something like that, but since it was more than a half a year, we round up. Questions on this slide? Feeling okay with this one? All right, next one. Bacterial growth. 2 hours after bacteria were introduced into a culture, the population was 256 bacteria. 5 hours after that, the population was 541. What will be the population 24 hours after the start of the experiment? And we started you off with an equation, y equals a e to the bx. Okay? Y is the population of the bacteria, right? Number of bacteria. What is A? Well, let's make it easier. Let's start with X. X is our what? Our time, right? How many hours? Okay. B is our growth factor, right? How much we're growing. And remember back to last year when you did these problems, what was your A? What was your A initially? Or what is your A from last year? Anybody remember? A is your initial population. How many you started with? Okay. All right, so we've got two situations here. We know that 2 hours after they were introduced, the population was 256. Okay? So we have 256 bacteria. We don't know how many we started with, and we know that it was after 2 hours, and we don't know what our growth factor is. We have a second equation, or a second piece to this, that says 5 hours after that, population was 541. Okay? So 5 hours after that means 7 hours into the experiment, right? Okay? So we have 541 bacteria. We don't know how many we started with, but we know 7 hours after we started, we have some growth factor. Okay? So how do we figure out what A and B are? You have two equations and two unknowns. What can you do? Basically try to solve for one variable and substitute it in, right? Okay. So it doesn't matter which one you start with, but if we're trying to get the A by itself here, then 256 over e times to the e to the 2b is A. Just divided to get A by itself. Now if I sub this into this A, I should be able to figure out what B is and then eventually find out what A is. So 541 equals my 256 over e to the 2b times e to the 7b. I have e to the 7b over e to the 2b. What do I do to simplify that? We cancel them and we'll end up with e to the 7b over 2b. So we have an e to the 5b. Now we want to get that e to the 5b by itself, so we divide. Now we have e to the 5b. We want to get to the b, and it's an exponent. What's the inverse of exponential? Logarithm. So we take a natural log. Be careful to make that a b and not make it look like a 56. So on the right-hand side, we get a plain old 5b. On the left-hand side, the natural log of 2.133, etc., is natural log of answer 0.748. We divide by 5. We get our growth factor, 0.1496, or 1.15. I'm going to keep it as 0.1, yeah, 0.1496 is going to be rounding to 3 places, 0.15. Almost there. Okay, now we just have to figure out what a is. So if we plug that back in, 256 divided by e to the 2 times 0.15, right? This is that 0.15 we just found out. We'll take 256 divided by e to the 2 times our answer from before. And we get 189.7 bacteria, so 190 bacteria. A lot of work, right? We still haven't answered our final question. So what's our final question? Yeah, how many after 24 hours, right? Okay. So to find out how many there are after 24 hours, all the hard work's done. We have our initial problem of y equals, our new a is now 190 times e to the something b, right? We don't know what x is, but our b is 0.15. And we want to know how many will we have after 24 hours. So y equals, yeah, so we're putting 24 in for x to figure out what y is going to be. Okay, so e to the 0.15 times 24. And then we're taking that number times 190. And we get 6,953, actually 54 bacteria. That should be 36.598. Or at least that's what I got when I did e to the 0.15 times 24. Okay? Marathon problem. So you had to come up with the equation based on 2 pieces of data, and then, or 2 points, and then figure out what the final result is. All right, questions on this one? Okay, last example. This one's logistics. So it's going to be something like that S-shaped curve that I talked about earlier. Okay. Logistics curves occur when we have disease. It also occurs when you have a population growth, because you soon start to consume all of your resources and no longer have space and so forth, and so part of your population can't continue to grow as fast. So, state game released 100 animals into a game preserve. The agency believes the carrying capacity of the preserve is 1,200 animals, and that the growth of the herd can be modeled by the population at any time t is 1,200 divided by 1 plus 8 e to the negative 0.1588 t, where t is measured in months. How long will it take for the herd to reach half of the preserve's carrying capacity? So they do things like this in Yellowstone, and they say, okay, we have bison. How many bison can we have in our environment without them getting overrunning the place, overgrazing, and having disease because of too close a proximity and things like that? And so then they cull part of the herd every year. They round up the buffalo and cull part of the herd every year, or most years. So we want to know how long it's going to take. We're looking for t until it reaches half its carrying capacity. So what's half of its capacity? 600. So we want that 600 to be this guy. So now we just have to unwind this equation. So we're trying to get to this t eventually. How do we solve a fraction equals a fraction? Yep, cross multiply. We can take our 600 times this 1 plus 8 e to the negative 0.088 t. And set that equal to 1,200. But rather than distribute that 600 into everything, are you okay with me dividing by 600 right away? Okay. I'll have a 1 plus 8 e to the negative 0.1588 t equals 1,200 divided by 600 is 2. So I just divided by 600, dividing by 600. Okay. Now I want to get this stuff by itself, right? So we'll subtract 1 from both sides. And we get 8 e to the negative 0.1588 t will be equal to 1. Okay? Still trying to get the t by itself, but there's an 8 hanging out in front. So we divide. So e to the negative 0.1588 t will be 1/8. And now how do we get rid of? Yep, we use a natural log. So the natural log of e to the negative 0.1588 t will be the natural log of 1/8. So natural log of 1/8 gives me negative 0.2 or 2.078 or 79. And we want to get that t by itself, so we'll divide. And we get 13.09 years. So 13 years, they'll be halfway to capacity. Now, do you think it's going to take another 13 years to get to capacity? No, why not? Not linear, right? We're talking about a logistics curve. So it's rising faster than a 1-to-1 ratio. Okay. All right. Questions on this slide? All right. So there's your assignment.